Mathematics is the search for patterns, and for the explanations as to why those patterns exist. It is a structural language used to uncover the logic built into the natural world. Take this sequence: 1, 7, 19, 37, and 61. At first glance, these are just digits on a page, but a specific, invisible rule forces them into this exact order. To find that rule, we have to look past the arithmetic and visualize these numbers as physical geometry. We begin by mapping the sequence spatially. The number 1 is represented here as a single point. Surrounding that center point with a ring of 6 new dots brings our total to 7. A second outer ring of 12 dots expands the shape to 19. This is the rule of the hexagonal number sequence. We are building expanding, flat hexagons by continuously adding multiples of 6 to the outer edge. This rule allows us to predict the next steps. By adding the next multipled 6, 36, to the previous total of 91, we find that the seventh shape contains exactly 127 dots. This two-dimensional pattern is perfectly consistent. However, these flat shapes can be rearranged to occupy a new kind of space. Consider what happens if we change the operation. Instead of listing the numbers, we will add them together sequentially. We start at the beginning. 1 equals 1. Adding the first two numbers in the sequence, 1 and 7, gives us 8. Adding the third number, 19, brings the total to 27. And adding the fourth number, 37, results in 64. The results, 1, 8, 27, and 64, are all perfect cubes. They are the products of 1, 2, 3, and 4 cubed. A moment of wonder. This creates a geometric curiosity. Adding a series of flat two-dimensional values has mathematically generated a three-dimensional volume. To understand why this happens, we have to look at the summation as a physical construction. Here are the first 4 hexagonal grids, laid out as flat layers. When we view these from a three-dimensional perspective, the relationship between the shapes changes. As we perform the summation, these flat hexagonal layers lift and stack directly on top of one another. The jagged, uneven edges of the different size layers are not random. They function as interlocking components. When combined, the layers snap together to form a solid, perfect cube. This demonstrates that a sequence of flat shapes can serve as the architectural blueprint for a three-dimensional volume. This geometric transition is proof that mathematics is a deeply interconnected system. We see this same logic in other sequences. Adding a string of one-dimensional odd numbers, 1, 3, 5, and 7, creates a perfect two-dimensional square of 16 dots. These patterns of space-filling efficiency are common in nature, where simple growth rules allow structures to expand while maintaining perfect geometric alignment. Mathematics provides the map for these transitions, showing how structures build upward from simple lines into complex realities. We can use this understanding to solve problems without performing the long-form math. If the sum of the first 4 hexagonal numbers forms a 4x4 cube, what is the sum of the first 5? Because we understand the blueprint, we know the answer is 5 cubed. The total is 125. When we treat mathematics as a search for these patterns, we can see the underlying logic in the world around us.